Good morning, students. Myself K. Lakshmi, Assistant Professor in the Department of EEE, Chebrolu Engineering College, Lecture 34, Unit 3, Magnetostatics and Ampere's Law. Topic: Solved problems on magnetostatics. In the last classes, we discussed about the theoretical part, whatever magnetostatics, that is Biot-Savart's law, and applications of Biot-Savart's law, and also discuss about the Ampere's law and its applications, and a point form of Ampere's law also we discuss it. Now, basing on that concept here, in this section we discuss about the problems, that is determination of magnetic field intensity for a circular coil solenoid like that by using Biot-Savart's law and Ampere's circuit law. Now let us discuss about the first problem. A circular coil of radius 5 into 10 power minus 2 meters and with 40 turns is carrying a current of 0.25 amperes. Determine the magnetic field of the circular coil at the center. So as in the problem, the given values are radius of the circular coil 5 into 10 power minus 2 meters, and the number of turns of the circular coil, that is 40, and current carried by the circular coil is given by 0.25 amperes, and magnetic field is given by B is equal to mu naught Ni by 2A. So this is the expression we have discussed in applications of Biot-Savart's law. By using Biot-Savart's law, expression for the magnetic field intensity of a circular coil is B is equal to mu naught Ni by 2A. Here mu naught is a constant value, that is equivalent to 4 pi into 10 power minus 7 Henry per meter, and number of turns 40, and the current is given in the problem, that is 0.25 amperes, and A 2A, that is 2 into radius of the circular coil, that is 5 into 10 power minus 2 meters. By calculating these all values, the magnetic field intensity B is equal to 1.2 into 10 power minus 4 Tesla. So this is the final value of magnetic field intensity, and T is a Tesla is the unit of B. Now, next problem. Determine the magnetic field at the center of a semicircular piece of wire with radius 0.20 meters. The current carried by the semicircular piece of wire is 150 amperes. Now, the given values in the problem are the radius of the semicircular piece of wire is 0.20 meters, and the current carried by the semicircular piece of wire is 150 amperes. Now, this is the expression of the magnetic field for a circular coil, that is B is equal to mu naught Ni by 2A. But here we cannot use this formula. Why? Because in this problem there is no value for N, that is the number of turns, and it is not a circular path, it is a semicircular piece. So with the help of Biot-Savart's law, the expression or the determination of magnetic field intensity is taken from Biot-Savart's law, that is dB is equal to mu naught I by 4 pi into dl sin theta by r square. Here the integral form of Biot-Savart's law is mu naught by 4 pi I by r square integral dl. Here integral dl means the total length. So for a semicircular piece having total length that is half of circular length, that is half of circumference, that is 2 pi r by 2. That is pi r is the length of the semicircular piece. So here, by substituting the mu naught by 4 pi I by r square, and the total length of the semicircle is pi r. So now substitute the values, that is mu naught and I and r here. Here there is a cancellation of r square and r. So finally this expression is written as a mu naught I by 4 r, pi also cancelled here. So mu naught value is 4 pi into 10 power minus 7 Tesla meter per ampere. And current is given in the problem, that is 150 amperes by 4 into, and the radius is a 0.20 meters. Now by all calculating these values, finally we get the 2.4 into 10 power minus 4 Tesla. Now next problem. In a particular region, there is a uniform current density of 15 ampere per meter square in the positive z direction. What is the value of integral d bar dot ds of when that line integral is calculated along a closed path consisting of three straight line segments from x, y, z coordinates. So here there is a closed path traveling from 4d comma 0 comma 0 to 4d comma 3d comma 0 to 0 comma 0 to 4d comma 0 comma 0, where d is equal to 20 centimeters. So in this problem, the given values are uniform current density, that is J is equal to 15 ampere per meter square, and we have to calculate the integral b bar dot ds value. So how we solve this problem? So this is the figure represents the uh, diagram based on the given values of the problem. Here these are the three coordinates x, y, and z, three coordinates. This is the origin point, and this indicates the direction of current density. That is, the current density is along z direction, that is given in the problem in a positive z direction. So J is equal to 15 ampere per meter square, that is along z axis. Now a closed path is starting from 4d comma 0 0 to 4d comma 3d comma 0. So here it is the starting point. Now it is traveling from 4d comma 0 comma 0 to 4d comma 3d comma 0, and finally next origin, and again 4d comma 0 comma 0. Basing on these three coordinates, we can easily measure the value of 0 comma 3d comma 0, this value also. Okay, now whenever we apply the Ampere circuit law, there is a main condition, that is we have to take in a closed path. Here this is the closed path, that is from point 4d comma 0 comma 0 to 4d comma 3d comma 0 to 0 comma 0 comma 0 to 4d comma 0 comma 0. So this is look like a triangular shape. So this is a very important point. So next we have to solve this problem. So the closed path is a geometrical figure which is equivalent to triangle. So the area for the triangle is half into base into height. So the base height and or values 4d and 3d. So area is equal to 1 by 2 4d comma 3d, which is equal to 6d square. So here the problem D value is equal to 20 centimeters. To convert the into meters, that is equal to 0.20 meters. Now substitute the value here, that is 6 into 0.20 meters whole square, which is equivalent to 0.24 meters square. Since the loop is orthogonal to current density, we are able to get away with saying that as a relation between current and current density is I is equal to J into A. Here J is a current density. So J is equal to 15 ampere per meter square. And the area, already here we have to find, that is equivalent to 0.24 meter square. By multiplying these two values, the resultant of current value is 3.60 amperes. Now we have to find the value of integral b bar dot ds. But actually, we study Ampere's law as integral h bar dot dl is equal to I. So the same expression we have to convert in terms of magnetic flux density as integral b bar dot ds is equal to mu naught I enclosed. Just for a change here, so B value can be expressed in terms of H as B is equal to mu H. So by replacing B by H, so integral B bar dot ds value is equal to mu naught I. So mu naught value is constant, that is 4.10⁻⁷. And I, that is current value, here we also find that already. Now substitute these two values. The resultant value is equivalent to 4.52 into 10⁻⁶ Tesla meters. So here, this is the final result of integral b bar dot ds. And the next problem. The figure shows a cross section across a diameter of a long cylindrical conductor of radius A is equal to 2.00 centimeters, carrying a uniform current of 170 amperes. What is the magnitude of the current magnetic field at radial distances? That is first problem at r is equal to 0, and B, that is r is equal to 1.00 centimeters, and C, that is r is equal to 2.00 centimeters, and r is equal to 4.00 centimeters. And the solution of the problem is, before we do this problem, we have to know the what is the expression for the determination of magnetic field intensity for a circular coil. So here there are two cases. One is R less than A and another one is R greater than A. For R less than A case, the magnetic field that is inside the wire. Now the expression is B is equal to mu naught IR by 2 pi r square. And another case is that is outside the wire, that is R greater than A. For this, B is equal to mu naught I by 2 pi r. Now we have to calculate the magnetic field intensity exactly at r is equal to 0. Now substitute this B is equal to mu naught IR by 2 pi a square. By substituting r here 0, then B value becomes to 0. Similarly, at r is equal to 1.00 centimeters, that is 0.0010 meters. Now substitute the values of r and A here, that is B is equal to mu naught IR by 2 pi a square. Mu naught value is 4 pi into 10⁻⁷. I is the current, that is 170 amperes, and R is equivalent to 0.0010 meters by 2 pi. A value is given in the problem, that is 0.0020. By calculating all these values, the resultant value is 8.50 into 10 power minus 4 Tesla. Now, magnetic field intensity, that is at R is equal to 2.00 centimeters, is equivalent to 0.0020 meters. B is equal to mu naught IR by 2 pi A square. So here mu naught value is 4 pi into 10 power minus 7 Tesla meters per ampere, and I value is 170 amperes, and the R value is equivalent to 0.0020 meters by 2 pi A square value is 0.0020 meter whole square. By calculating these all values, the resultant magnetic field intensity at R is equal to 2.00 centimeters is 1.70 into 10 power minus 3 Tesla. Now the last problem in this case is at R is equal to 4.00 centimeters. In meters, it is equivalent to 0.0040 meters. So B is equal to mu naught I by 2 pi R. Mu naught value is 4 pi into 10 power minus 7 Tesla meter per ampere, and I is current 170 amperes. 2 pi R value, that is 0.0040 meters, and the resultant value at R is equal to 4.0 is 8.50 into 10 power minus 4 Tesla. So this is the solution of the problem for different positions of R, that is R is equal to 0, R is equal to 1 centimeter, and R is equal to 2 centimeters, and R is equal to 4 centimeters by given current and values. Now the next problem is the plane y is equal to 1 carries a current density, that is K bar is equal to 48 ampere per meter. Find H at A 0, 0, 0 and B 1, 5, minus 2. So before we discussing this problem, first we have to discuss the diagram. So this is the coordinate axis, and this is the position indicates the y is equal to 1 plane, and in this case the K bar value, that is here the current, that is K bar is along in a AZ direction, that is we have to understand by this expression K bar is equal to 40 AZ bar. So this is the Z bar direction. So this is the K bar value, that is equivalent to 40 AZ bar. Now the magnetic field intensity at a point A comma 0, 0 value is expressed as, so it look like a application of Ampere's law, that is a determination of magnetic field intensity for an infinite sheet of current. So that is expressed as H bar is equal to 1 by 2 K bar cross AN bar. So here the K bar is indicates the direction of the current, and AN bar is indicates the it is a direction of the normal to current sheet at point A. So it is a K value is given in the problem, that is 40 AZ bar, and AN bar is equivalent to minus AY bar. Why? Because it is along at Y is equal to 1 plane. Now 1 by 2 40 AZ bar cross minus of AY bar. As according to vector identity properties, AZ cross AY bar value is equivalent to minus AX bar. So here there is already a negative value. So minus AX and minus ax minus minus plus ax. So h bar value at point A is equal to 0 is half 40 ax bar, that is a 20 ax bar. That means the magnetic field intensity is along x direction. So it is clearly the direction of the current is along y and the sheet is on y is equal to 1 plane. Automatically the magnetic field intensity is along x direction. Now we have to find the magnetic field intensity at the point B 1 comma 5 comma minus 2. So here the y value, that means the plane, the right of the plane value y is equal to y coordinate is 5. So that means here the plane is along AY direction. So simply by taking AN value as a AY here, so 40 AZ bar into AY bar, that is equal to AZ bar plus AY bar. Already we discussed that, which is equivalent to minus AX bar. So 40 by 2 is equal to minus 20 AX bar ampere per meter. And the next problem, in the region 0 less than or less than 0.5 meters in a cylindrical coordinate, the current density is J bar is equal to 4.5 e power minus 2r AZ bar ampere per meter square, and J bar is equal to 0 elsewhere. Use Ampere's circuit law, find the value of H bar. So initially the expression for the current in terms of current density is I is equal to integral J bar dot ds bar. In this expression, ds is the surface area. So this surface area in a cylindrical coordinate system is equal to r dr d phi az bar. Here, why? Because the z is in az bar direction. So substitute the values of ds and r values here. I is equal to, so here it is a cylindrical coordinate system. In a cylindrical coordinate system, r and theta phi are the variable, z theta phi are variables. So here there is no z component here, and az dot az value becomes to 1. So finally here only r and phi values. Already we have know the limits of r and phi. R values is varying from r is equal to 0 to r, and phi value is 0 to 2 pi. Now, so 4.5 is a constant value. Here r into e power minus 2r into dr. Here the d phi value is constant, and that value applying for integration phi is equal to 0 to 2 pi, it is equivalent to 2 pi. It is clear. Here r into e power minus 2r dr is look like a integral by parts method. So by applying integration by parts method for this r into e power minus 2r, this is equivalent to integral phi is equal to 0 to 2 pi d phi. Now by applying integration for this r part by integral by parts method, so r into integral e power minus 2r dr minus integral 1 integral e power minus 2r dr into dr from limits 0 to r. So 4.5 into, already I said that the integral value of this is equivalent to 2 pi, and r into integral of e power minus 2r value is also equivalent to e power minus 2 r by minus 2 minus of integral minus 2r by minus 2 into dr from limits 0 to r. Now by substituting these values, it is equivalent to 9 pi by 4 1 minus 2 r e power minus 2 r minus of e power minus 2 r amperes. So we have to substitute the r value that is given in the problem from 0 to 0.5 by taking r is equal to 0.5 here, which is equivalent to current value 1.8676 amperes. Consider when this is a closed path with r greater than or equal to 0.5 such that then enclosed current I value is also becomes to 1.8676 amperes. So this is the magnetic field intensity for r greater than or equal to 0.5 meters. That is equivalent to from Ampere circuit law, integral h bar dot dl bar is equal to I. So here the h bar value we have to write as a h5 because the values along r and z are 0. It has only the h has only along phi direction, so it has a variable only h5. Similarly, in a cylindrical coordinate system, dl value having only terms along phi direction, that is equal to r d phi, r d phi a phi. Here also h phi a phi. By dot product, a phi dot a phi value is equal to 1. So h bar dot dl bar value is equal to h phi r d phi is equal to I. So here r is constant and integral d pi with limits 0 to 2 pi value is equal to 2 pi into h pi. As already we calculated the current value I is equal to 1.8676, substitute here, and h pi value is equal to 1.8676 by 2 pi r. Again here by substituting the pi value as a 3.14 and except or by calculating all these values, it is equal to 0.2972 by r. Now here it is a magnitude. Now the vector of h bar is equivalent to 0.2972 by r into unit vector that is along phi direction a phi bar ampere per meter for r greater than or equal to 0.5 meters. So these are the various models of problems in magnetostatics, basing on magnetostatics and ampere circuit law. In the next class, we discuss about the magnetic force. Okay, thank you.